experimental studies shows that the velocity of the heat, which is a vector, is given by some constant, which is the heat conductivity, multiplied with the gradient of u. The gradient of u is the vector of three components, which is in the first component the partial derivative of u with respect to x. The second component, of course, is then the partial derivative of u with respect to y, and the third component is the partial derivative of u with respect to z. This vector, the velocity of the heat vector, is an important vector which we are going to use a little bit now. If we consider the same example as before, with the only difference that the boundary conditions are changed. Instead of knowing the temperature in the boundary here and here, we now have no information about the temperature other than the knowledge about the velocity of the heat in these points. Because if we also have insulated ends, endpoints of this rod, then the velocity of the heat must be equal to 0 in this point. This is another type of boundary condition which is very usual from a physical point of view. And as before, we want to know the value of the temperature as function of x and as function of the time t. As before, we have this partial derivative, partial differential equation, and the velocity is given by this expression. V is equal to sigma multiplied with, in this case, because it's a one-dimensional problem, it's only a scalar, namely the partial derivative of u with respect to x. So in our case, the velocity v is equal to 0 on both the starting point x equal to 0 and x equal to L. We can make a very similar calculation as we did in the case when we knew the boundary condition. And the calculation leads us to the following expression. U of xt is equal to this infinite series. N goes from 0 to infinity, not 1 as before, but to infinity, but 0 to infinity. And we have this series. The only difference is that now we are changing the sign with cosine, and an turns out to be the Fourier cosine coefficients of the function f of x, which is the initial temperature. And these coefficients are given as follows. The starting value a0 is equal to 1 over L multiplied with the integral from 0 to L of f of x dx, and for n larger than 0, an is equal to 2 over L multiplied with the integral from 0 to L of f of x cosine to npx over L.